Um, Hello everyone, it's my great pleasure to introduce our speaker, Yifan Quan. Yifan started his undergraduate when he was just 15 years old at University of Science and Technology of China, and he then did master at Zurich and PhD at Paul Institute with Dr. Patrick Halter and Professor Wenke Batch. And 2 years ago, he started postdoc research in Professor Bob Griffin's group at MIT. And this year, he has published several papers about various topics. And today, he will be talking about coherent chirped pulse DNP. And Yifan, the mic is yours.
Yeah, thank you for the kind introduction. Does everyone hear me well? And let me see, put this on slides. Yeah, so is the slides showing okay?
Yes, it is.
Yeah, it looks good.
Okay, so I'll start. First, I would like to thank the organizer for giving me this opportunity to present some of our recent work on coherent DNP using chirped pulses. I'll start with a brief introduction on what is DNP and in particular, why we want to study pulse DNP, and then show you some of our recent theoretical development of DNP using chirped pulses. And finally, I'll show some quite exciting, very recent experimental result that we obtained. So what is DNP? As you know that both EPR and AMR are magnetic resonance techniques. They measure the population difference of the two Zeeman levels, for example. For localized distinguishable spins, the polarization can be calculated by the Boltzmann distribution. However, the German ratio of the electron and the nuclear spin are largely different. Even for proton spins, the ratio is about 660, and for other species of nuclear spins is even a higher value. That makes EPR and AMR actually working at quite different regimes. For example, EPR is typically working with microwaves from several gigahertz up to several hundred gigahertz, while AMR is typically working with several hundred megahertz radio frequency. And also they have so for EPR, all the electron spins and the nuclear spins also have a quite different time scale that I'll mention. AMR is a fantastic tool to solve a lot of problems like material studies and biostructural studies. However, one limiting factor of AMR is the poor sensitivity due to for example, the low polarization of the nuclear spins. So then we start to think, electron has a much higher polarization. Can we make use of that and transfer the electron polarization to the nuclear spins? And this can be done with the dynamic nuclear polarization. So what we do is we introduce some polarizing agent into the system. For example, radicals, some free electrons. What you need is, and then you want to manipulate the electron spin. So what you do is, you need to talk to the electron spin. So you use microwave to irradiate the nuclear spins, mitigated by typically the hyperfine coupling. The electron polarization can be transferred to the surrounding nuclear spins. And then this polarization can be distributed to the whole bulk via the spin diffusion process. And as I mentioned, the time scale for electron spin and the nuclear spin are largely different. The electron typically has a much shorter spin lattice relaxation than the nuclear spins. That allows fast recovery of the electron polarization and allow that one electron can serve many nuclear spins or polarize many nuclear spins. And here shows an example of DNP enhanced spin echo signal, MR signal, with 30 minutes acquisition and compared to the thermally polarized signal with 24 hours signal acquisition. So of course, there are a couple of different DNP mechanisms to polarize the nuclear spins. The first family is called the solid effect, which works for a simple electron coupled to one nuclear spins. It relies on the flip-flop between the electron and the nuclear spins, where you irradiate at the forbidden transition of the EPR, which would be the term familiar to the EPR community. And for this, we typically use monoradicals, for example, like tritose and BDPA. Also, transition metals like gadolinium and manganese. The second family is the Overhauser effect, which relies on the cross-relaxation between the electron and the nuclear spins. This typically we observe in liquid and conducting metals. However, recently we also saw this effect in insulating solid like BDPA in polystyrene or in also terphenyl. You see that when you irradiate at the EPR transition, by saturating the EPR, you have enhancement by the cross-relaxation. And the third family is so-called cross effect, which relies on a three-spin system. It relies on the triple spin flip, where you have a flip-flop between two electrons, and the electron Larmor frequency difference corresponds exactly to the nuclear Larmor frequency. The flip-flop of the electron spin pair can induce a flip of the nuclear spin. For this, we typically use biradicals, for example, total pole, amipole, temperature, and there are a lot more other biradicals that have been developed for the last decades to do better cross effect. However, most of the DNP right now are still done with CW, so continuous wave microwave irradiation. And a big problem of that is the efficiency of CW DNP scales down or scales quite poorly with the magnetic field, and you need the high magnetic field to reach to gain AMR resolution. Also, CW is a quite antique word. For the EPR community, people still do CW AMR. Sorry, people still do CW EPR, but I believe most of the audience had no experience with CW AMR anymore. So as you know, that like pulsed EPR and pulsed NMR, with the ability to manipulate the amplitude, the frequency, and the phase, you can do a lot of fantastic experiments for both EPR and NMR. So that applies to DNP also. For example, the first there are a couple of families of pulse DNP has been developed. The first one is the so-called NOVO. So it's short for nuclear orientation via electron spin locking. So what you do is you first apply a pi-half pulse, and then you lock it with a locking pulse. And when the effective field or the Rabi field of the locking pulse matches to the nuclear Larmor frequency, you can have the polarization transfer. So this is very similar to the CP for the AMR community, except that here we don't have a pi-half pulse on the nuclear spins. So we are still having the nuclear spin, the lab frame, polarizing along the Z direction to keep the polarization. And there are a couple of other variants of the NOVO, for example, like overessence NOVO and the ramped amplitude NOVO, which this one would be straightforward for the AMR community, where when you do CP, you also modulate the amplitude to gain CP efficiency to polarize more spins. And forgot to mention that for the pulse DNP, we mostly also use monoradicals like tritose BDPA. The second family is the so-called time-optimized pulse DNP. So instead of using long pulses, we use a train of pulses. For this, when you match the modulation frequency of the pulse and the effective field of the pulse to the nuclear Larmor frequency, you have the polarization transfer. And for this, also there has been a couple of other variants that have been developed for the last couple of years, very recently, such as the XX, TPPM, and the BEAM DNP. And I want to mention that for pulse DNP, the problem of the efficiency scales down with the magnetic field can be strongly mitigated by the capability of manipulating the pulse and allowing to reduce the power of your microwave also, which I'll talk later. So for today, I will be mainly talk about another family of pulse that's using frequency sweeps. Namely, there are three pulse schemes I will be talking mainly today. First one is the integrated solid effect, which in the rotating frame is a broad sweep from -infinity to infinity, crossing both solid effect matching conditions, covering all the spins. And the stress solid effect is half of that. We stop at the EPR center. Well, the third one would be ADFS solid effect, where we use quite narrow chirps, just around one of the matching conditions, and it can even be narrower than the EPR line width. Just a quick recap of the history. Integrated solid effect is actually not something horribly new. It was first invented by Wenkelbach and colleagues in the 80s already, and they actually gained an enhancement of 5,500. Of course, this is not done with the thermally polarized electrons. This was done with photoexcited transient state. At the time, people were doing ASE with field sweeps. But nowadays, with the advances of technology, these things can be much easier done with using AWG, so an arbitrary waveform generator, to apply just a simple frequency sweep. And this actually makes life much easier to run experiment, just going through the frequency ranges. And you can measure a lot more points. And this actually leads to the discovery of the SSE and ASE. When you do a lot of field profiles, we find that, well, instead of doing ASE going through everything, when you chirp at the side, right, only covering half of the ASE range, it's actually more efficient. And later on, we find that just narrow chirps around the solid effect matching condition is also can be more efficient than ASE. Then this brings us the question, what exactly happens when one just applies random arbitrary sweep at anywhere? In order to answer these questions, so we sit down, carefully visit the theory, calculate the polarization transfer using the Landau-Zener theory to calculate the level crossing here and here. So of course, first we figure out that the ASE is going through both matching conditions. Well, SSE just stop at the center, just going through one matching conditions. So I'm not going to the details of how this was calculated, but we did the calculation and find we write down the polarization transfer ratio going through one matching condition and going through the subsequent matching condition as a function of Q, which is proportional to the omega-1 square over the sweep rate. And when we plot it, we found, well, mathematically, yes, the SSE can be a factor of 3 more efficient than the ASE, actually. And this has been confirmed by just numerical simulations using the SpinEv simulation package. And I also want to mention that for the analytical calculation, we consider a model of one electron spin coupled to many, many nuclear spins. So we can approximate the distribution of the hyperfine coupling to a continuum. Well, here we only working with a limited number of nuclear spins. Here is an example of 9 nuclear spins. I find the more nuclear spins you put, the curve getting more and more close to the theoretical calculation. And another very, very interesting thing that I find we think is we find the polarization transfer efficiency can be more than 1. And what does that mean, actually? If we, well, first we look at the definition. I want to remark the definition of the polarization transfer ratio is it's the nuclear polarization gain per pulse divided by the electron nuclear polarization difference. And I want to remark that it's always the difference between the electron and the nuclear polarization is transferred. In that case, a polarization transfer 2 just means if you start with electron polarization 1, nuclear polarization 0, a polarization transfer 2 means your electron polarization becomes 1 minus 2 becomes minus 1. So your electron polarization is simply inverted. And then you have a gain of nuclear polarization gain by 2. Of course, you cannot have one single nuclear spin becoming nuclear polarization 2. The polarization is distributed to all the coupled nuclear spins, so each one gain a nuclear polarization averagely 2 over number of nuclear spins. That's also the reason why the more nuclear spins you have, it's getting more close to the theoretical calculation, because if you only have one nuclear spin, you can maximally gain a nuclear polarization 1. So that's also why it's quite important to build a model with one electron spin coupled to many nuclear spins, or at least a couple of nuclear spins, which would be correspond to the realistic situation for DNP. And actually, this inversion of the electron spin polarization actually explains why it's more efficient to just stop. Here we show a nice movie by our PhD student Michael Mardini. That so here we plot the simulation results using SpinF simulation. Here we show the electron polarization trajectory during the Chirped Pulses, and here is the nuclear polarization. So in the beginning of the Chirped Pulses, you adiabatically rotate your electron magnetization to the Solid effect matching condition. And that here you have the polarization transfer happening. When it's efficient, your electron polarization can go to the other direction of the sphere. When the polarization transfer is larger than 1, and you have a gain of nuclear polarization. And then you further adiabatically rotate your electron spin polarization towards the second matching condition. And at the second matching condition, because here your electron polarization is becomes anti-parallel to your effective field already. So you have a negative electron polarization here. So you can think here as either you are polarizing your nuclear spin towards the wrong direction, or you can think that actually the nuclear spin polarizes your local nuclear spin polarizes your electron spin back to, you see the back to this direction. So you have a direct decrease of your nuclear spin. And this is also because your pulse is within a very short time that everything is still, so the spin diffusion, the nuclear spin diffusion hasn't kicked in yet. And then the next question is, well, can we experimentally see this inversion of the electron spin polarization? And this actually can be easily done with EPR measurement. So we modify the Han echo. So instead of using a hard pi-half pulse, we just replace it by the SSE DNP pulse. So which just adiabatically rotate your electron spin polarization to the 90 degrees to the transverse plane. And then we apply a pi-half pulse or a pi pulse to refocus so you have the polarization transfer during this DNP pulse, and you use a pi pulse to refocus whatever is left in the electron spin, and then measure what's left after the SSE pulse. And as I mentioned, it's always the polarization difference between the electron spin polarization and the nuclear spin polarization that is transferred. Then is well, obvious in the beginning when you don't have any nuclear polarization, you have a lot more polarization transferred, then you have already a highly polarized nuclear spin. So when your electron and the nuclear polarization equals to you have 0 electron spin polarization transfer. So in that case, we compare 2 cases where first we have a strong gamma B1. So you have a high polarization transfer. And we see that, yes, for the 2 cases, we see an inversion of the electron spin polarization. Well, when you do it with weak gamma B1, so you have inefficient polarization transfer, you don't see this inversion anymore. So this experiment, just a simple experiment, nicely showed that this inversion of the electron polarization. And this actually also explains why I like to use the word coherent DNP in this experiment, because you are really coherently manipulate your electron spin, not just only your electron spin, but your whole spin Hamiltonian density matrix during your DNP pulse. Now we have theoretically understand the what's going on when you apply a Chirped pulse. Oh, sorry, I forgot this slide. So we want to also compare to the gold standard DNP pulse DNP sequence novel. I'm not going to tell you how this was calculated in this well-written paper. But if you plot it as a function of the pulse length, you find that for novel, the maximum polarization transfer per pulse is about 1.3. And this is an experimental verification of the curve. And if you compare that to the ASE and the SSE polarization transfer, you find it is a factor of 2 more efficient than ASE, but you find the SSE can be much more efficient than novel also. And another very important thing is, well, when you apply a Chirped pulse, you're not irradiating at a single frequency. You are covering all the spin packets. Well, for all the other like typical single frequency irradiation pulse techniques, for example, novel, you are only using a fraction of your electron spins. So we did a couple of calculations for different EPR line widths. So here shows the example at Q band, so 50 megahertz proton frequency, and with different EPR line widths. For Tritle, it is about 3 Gauss in this field, which is still quite good, close to the case where I don't have any line widths. But you see that if you have a broader EPR line widths, the efficiency of this pulse of novel drops by quite some. Well, the Chirped DNP is actually, you are covering everything. So that's actually a huge advantage using Chirped pulses, I would say. Now we have theoretically understand what's going on with Chirped DNP. We want to experimentally verify our theory. So this was done with Triplet DNP at PSI, held by my former colleague Jakob. So instead of using stable radicals, we use photoexcited triplet state. So the sample we use is naphthalene single crystal doped with pentacene molecules. Here shows an example of a nice crystal that can be grown to large size also. So the pentacene molecule, upon laser excitation, can be excited from a singlet state to another singlet state. Well, most of it directly decays back, but part of it can go via intersystem crossing to a transient triplet state. Short-lived, will decay back, but at this triplet state, you have a larger non-thermal equilibrium electron polarization, and we can make use of this to pump it to transfer it to the nuclear spins via DNP. And the advantage is that this is independent or practically independent of the magnetic field and temperature. You can reach really high nuclear polarization. Like 80% would be the record we achieved. And another huge advantage is when you don't have laser light, or when you don't have photo excitation, you don't have paramagnetic centers in your system. That means also even in between the laser pulses, you don't have paramagnetic centers. And the paramagnetic center is typically the main source of your nuclear spin lattice relaxation. So that gives a really long nuclear T1 for the system, which is, well, here shows some values. And this is excellent for testing theories because you can really nicely study the build-up of your nuclear polarization, which is to study the polarization transfer efficiency per pulse. So we did a couple of field profile measurements as a function of a different gamma B1. And we find it nicely agrees to the theoretical calculation. And we'll summarize all the data points here. We find as theory predicts, the ASE has a peak, while the SSE just scales up with with gamma B1 and over the sweep rate. So this also tells us that we want to do SSE and with a strong B1 and slow sweep rate. And also will show that SSE is less challenging because you only have to sweep a narrower range than ASE. Now with the better understanding, we can give a better definition to separate the different chirp schemes. For example, ASE would be the broad sweep covering both matching conditions and all the spins, and SSE just covering one transitions. Well, ASE, which I'll talk later also, which would be actually a quite practical way to run DNP that's using very narrow chirps, getting rid of all the unnecessary parts and just use the parts that actually do something. And it can also be narrower than the EPR line is from a practical reason, which I'll show. Okay, so next, we want to push the experiment to a higher field, of course, to an more relevant field. Well, we are not yet there. So we did a set of experiments at the Hyper instrument in Tallahassee in the Mag Lab. It's a W-band 94 gigahertz pulse EPR instrument. I would say it's a high field for EPR, but it's still low field for NMR, but we are slowly pushing there. It's a very beautiful instrument. It was developed by Graham Smith in St. Andrews. And it's well, it uses a microwave source of a kilowatt EIK, runs with a helium flow cryostat. Well, which is a very luxury thing to run nowadays with the price of the helium, liquid helium. It can go to about 4 or 5 Kelvin. Electromagnet goes up to 9 Tesla, and we are working with G equals to 2 radicals, so we don't really need this high field. We stop at about 3.4 Tesla. It's equipped with a nice key set, 12 gigasample per second AWG, allowing us to do all kinds of fancy chirps. And this is the sample stage for the spectrometer. Use a fluorine plastic EPR tube. Here shows the NMR coil wrapped inside of these Teflon tapes. Just a spoiler alert, the best enhancement we have obtained is 496 using 10 millimolar tritium in DNP juice at 70 Kelvin. But the only reason that we did at 70 Kelvin instead of 80 Kelvin is just because we can, just to show off with helium. Well, this enhancement will calculate into time. This would allow an experiment that would take well, almost 700 years to be done with in one day. That becomes realistic. And also, I would say this value will be even more drastic that I will show later. And also, I want to mention that this is the second time we run this pulse DNP experiment in the Mag Lab. The first time was a couple of years ago when we don't really understand what's going on when we apply a chirp pulse that we were trying, and we discovered this SSE effect. But at that time, we only obtained an enhancement of about 70. And now we have a lot better improvements. Also, I want to mention that at that time we were using kilowatt EIK, and now we only have about 250 watts or 300 watts due to the aging of the EIK, but we get much better enhancement. So for this, I want to point out that by have a better understanding of the spin dynamics of what's going on with your spin system, you can much better do your DNP or any type of experiments, I would say. Of course, it requires a lot of optimization before reaching that enhancement. As I mentioned, from a practical point of view, well, from theoretical point of view, the most efficient way is to run SSE covering everything. However, from practical point, you are often limited by a lot of things. For example, the the duty cycle and the maximum pulse length of your microwave amplifier. So for example, when you have a fixed pulse length, the broader you sweep, already you are covering more electron spins. You are actually reducing your sweep rate. Sorry, you are actually increase your sweep rate, which would be reducing your polarization transfer efficiency. So typically there will be then having an optimum sweep width or sweep rate, which would be around ASE, and this can be even narrower than the EPR line width. And of course, if you have the stronger B1 field you have, the broader you can sweep, covering more spins. So this will be then the peak will be moved to the right side, go towards the SSE situation. Well, when you don't have power, the peak shift to the left, and it might even be more efficient not chirping. If you have in the extreme case would be CW. And here shows an example of a field profile that we took. The dashed line is the microwave power. You find that at one side we have more power than the other side, and show that when you have power, it's more efficient to do the chirp. Well, when you don't have power, it might be worthwhile not chirping. Or I mean, we are doing with fixed power. This field profile was done with a fixed with chirp. So it's probably at here you should chirp with less width. And another thing that I want to mention is DNP not only enhances your NMR signal, but it also reduces your repetition delay or the rise time, as shown here. Well, with microwave on and off, this is already normalized. So at here you have enhancement of 496. But if you measure this just microwave on off at some time here, if you might have enhancement larger than 1,000. For extreme case, we measure enhancement. Well, we didn't call it enhancement, but let's say signal on over signal off, we get a ratio larger than 2,000 even. And of course, if you compensate the rise time, sorry, if you also consider the rise time shortening, just do the calculation of combining the enhancement and the shortening of the rise time, you get a kind of a figure of merit or whatever it's called, even higher value. Here is 670. That is even more than the ratio between the electron, electron spin polarization to the nuclear spin polarization. So you can gain above that just by the signal to noise resolution. Another quite interesting is we studied the temperature dependence of the DNP enhancements and find a significant drop from 110 Kelvin to 130 Kelvin, actually. Well, this appears to be some drastic phase transition, apparently. However, we know this is now the glassing point of the matrix we've discussed. So because that's quite well measured and documented at around 150 Kelvin. So this is already quite below. So we are not sure what's happening here, but this is something we want to further investigate. And this significant drop was also reproducible for the 10 millimolar sample. So this is not just one sample we saw this. And I also want to mention that the temperature dependence of DNP actually can be quite complicated, not straightforward. And here this is something else, but also just in general. For example, if you think that if you cool down your temperature, you will have an increase of your electron T1, which is bad for your DNP because now you have to wait a longer period time to have the electron recover to its original polarization. But you also have an increase of your nuclear T1, which is good for your DNP enhancement. So it will be something complicated, and these values also varies drastically between sample to sample with different matrix and different concentration of radicals or type of radicals. So you wouldn't be surprised that for each single sample you have a different temperature behavior, and it could also be that the temperature is not just straightforwardly going up. It could be having some optimum spin temperature, optimum temperature to run DNP. So this is also something we want to investigate in future. So yes, with the careful optimization, we have achieved the enhancement of this value. Well, it's actually would be a more drastic shortening of time if you consider the shortening of the repetition delay. And it was done with 40 megahertz sweep in microsecond microwave pulse with a 1.2 millisecond repetition delay. So this corresponds to a duty cycle of 1%. So if you consider a 250 watt microwave, it's averagely only about 2.5 watt, which is still about a factor of 10 less than modern date gyrotron. I would think this is because for pulse DNP, you are really using your microwave in a smart way where you irradiate your microwave at the time where you need your microwave. And then you have a period that you wait for the recovery of the electron spin polarization. And we also ran a couple of different other samples, for example, with the fully proton in water, find although, well, it still have a decent relaxation, still decent, very decent enhancement, although lower, but a lot more protons. Anyway, hopefully have convinced you that it is advantageous to run pulse DNP, especially towards high fields. Of course, it still needs pulse DNP is still quite in its infant stage for high field, and it requires a lot of development, particularly for instrumentational development and also methodology development. Just a brief summary, we have now a much better understanding of Chirped DNP, and find the SSE or ASE can have a potentially a factor of 3 more efficient than running ASE, and the ASE could just narrow chirp could be the most practical way to run DNP experiments. And we have experimentally verified our theory by Triplet DNP, and we are pushing it to higher fields, and we reach a record polarization at this field, I think, of about 500. And as I mentioned, by theoretically understanding the spin dynamics, you can better design your pulse DNP experiments and develop more better pulse schemes. Of course, I would like to give a lot of credits to everyone who has been involved in this work, to our group members and my former colleagues who helped with the Triplet DNP experiment, and people in MagLab, especially Manoj and Jerry, who helped setting up the spectrometer ready for DNP experiments and helped get the W-band DNP experiment done. And thank you for your attention. Happy to answer any questions.
Thank you very much, Yifan. It's a very excellent talk. I believe there are lots of questions from our audience, and I will start with one simple question. When you say your power is 250 volts, do you measure the power at the sample, or do you measure it right after the EIK? I think there will be a difference, right?
So that would be a question for the spectrometer, but I think it's documented in this paper that it's documented in this paper. I think they recently measured the power. I'm not 100% sure, but I think it's something outside of. I cannot say for sure. Maybe it's better.
Okay, I see from the chat, theory that power is measured at the EIK.
Okay, yeah. Yes.
Okay,
the
thank you.
To say this, yes.
Okay. Is there any other questions? Please raise up your hand or just text in the channel. Okay, well, we're still waiting for other questions. I may have another one. I see your build-up time is maybe several minutes. So do you see some heating effect at the sample?
Well, there's definitely heating of the sample, but I mean the heating would caused by the average power you put in, and if you compare that to the gyrotron, I would say it's still a lot less heating than a 20-watt gyrotron.
Okay. Yeah.
Yeah.
So there's one question in the chat.
Yeah.
Can we use pulsed DNP for detective diamonds at room temperature?
Yes, I would say there's no reason why we can't, and this is all something we want to try. That I think there are probably people trying these things already. If you look at Ashok, Adroy's, well, they were working with NV, but the principle would be the same.
Hope that answers your question.
There is a question from Graham Smith, I guess.
Okay, Graham.
You can unmute.
Hey, yeah, great talk. Really enjoyed it.
Thank you.
In terms of the build-up time, what do you think is the limiting step? I mean, what is is it the nucleus to nucleus, or is it just a coherent transfer of polarization?
I would think it's still the polarization transfer. The nuclear spin diffusion would typically be quite efficient, I would say. I would think. Because I did these calculations before, that if you calculate the concentration, let's say the average distance between an electron and another electron, and if you calculate how much time it would take from this to take for spin diffusion to diffuse this distance, I think it's well, it's in the order of milliseconds, or it could be less depending on the concentration, and and we are running with 1 millisecond repetition delay. So within this 1 millisecond repetition delay, I think it's quite efficient to diffuse all the polarization, I say, towards the whole bulk.
And so, do you think if you had your kilowatt, then it would improve that instead of the 250 watts, it would improve that?
Yes, I think you could further improve. At least you would shorten the repetition delay, or you should increase, let's say, shorten the rise time further.
I want to one last comment on the. I mean, it's really strange the fact that the DNP disappears completely. Are you sure you haven't got, at high temperatures? Are you sure you're not reaching 150 Kelvin, and that you just don't live in heating?
Yes. So yeah, it's so we measured here. It's not. It's we measured the enhancement about 20 here. It's still some enhancement. That's something we were also thinking, if, well, yes, we could have some heating, but we don't think it would be that drastic, about 20-30 Kelvin. It could. Well, this is something we really need to check. And it's, I mean, it's also a reading. I also have to check with Thierry and see how precise the temperature reading is, because you are also reading temperature from another location if it's not exactly the sample temperature. So if that could be well over. So this is something we are not sure. This is something we are not really sure, and we should do a bit more points in future also.
I mean, my suggestion would be for Thierry or yourself is check whether the sample becomes opaque at that point, that there's nothing being transmitted through it, and you just look at a surface reflection, because that's what happens at the glass transition. Nothing gets through; it's completely absorbing, and then I could imagine you'd have some massive drop off. Yeah. But then it would need a 30-degree. You need to be 30 degrees out with your temperature, which
yeah, which is
maybe not.
Yeah,
they're very impressive. As always from Bob's group.
Okay, thanks, Graham's question. I see Jennifer raised hand.
Hey, hello. Thanks for the nice talk. I was wondering if you investigated this rise time or build-up time as a function of the temperature, because you showed also experiments at different temperatures, and I was wondering how that would behave.
No, we didn't have that much time to do that many points. It takes time to do experiments. It's actually quite slow rise time. So
Okay, yeah, I was just curious. But this is at 70 Kelvin, this experiment.
Yes, most of the experiments are done at 70 Kelvin. The other temperature we just take long enough time to take one thermal and one build up fully polarized.
Okay. And then I have another question. What was the nutation frequency that you could generate in this experiment?
So let's see, I think we talk average, I would say like 20 megahertz, 20, 30 megahertz.
Okay. Thanks a lot. Thanks.
You.
Thanks, Jennifer. I see there's another question from Morgan again. Can we use pulse DNP for biological tissue samples such as skin?
Well, yes. I mean, DNP has been applied to a lot of bio samples, but well, mostly as long as you can freeze your sample. Nowadays, still people do it at like 90 Kelvin also. So it's been largely applied to biostructural studies, DNP already.
Okay.
You particularly pulse DNP, we are still developing that. We are moving to, because for NMR you need resolution, so you have to go to a high field, and right now the highest experiments we did is 140 megahertz. It's still relatively low for NMR fields. So we are pushing it. We want to do it at several hundred megahertz.
Okay, cool. We're waiting for other questions. I have one more. So have you tried to purposely reduce the peak power a little bit, and just to see how the enhancement change with the peak power? Because as you said, at higher frequencies, so we don't have such powerful amplifier or microwave source. So it would be nice if we can have similar enhancement with relatively smaller power.
Yes, we tried. We actually tried to do a little bit lower power, and well, it definitely decreases. I can't give you
how fast it decreases.
It's, well, generally from theoretical point of view, it decreases with the omega-1 square.
Okay.
But it probably won't be that drastic. Well, I don't have an exact value for the moment.
Okay. Is there any other questions?
But also, as mentioned, decreasing the power, you can kind of compensate by reducing the sweep speed also.
Yeah, of course. Yeah. And what is the sample volume in your case?
I would say 100 microliter, something like that.
Okay.
The sample tube is something like this.
Okay, if there is no other questions, so let us thank our speaker Yifan again, and thank all the audience for your questions and for coming along to our meeting. And we hope to see you in 2 weeks' time. Thank you.
Thank you.
Take care. Bye.
Thanks, Yifan. Bye.
Bye.